Okay, let's look at some of the properties of the Riemann integral. They mimic the properties of the antiderivative, but it's important that we understand the definition of a Riemann integral. So first, let's suppose that f and g are Riemann integrable. That is, they have Riemann integrals, and we're going to assume that k is a fixed non-zero constant. Then we can actually integrate the function k times f, and that will be equal to the integral of f times k. That is, we factor the k. Constants can be pulled outside the integral sign, which we do all of the time. And then secondly, the sum function f plus g is equal to what? The integral of f plus the integral of g. So what we're saying in both of these results is that kf is integrable, and it equals that. F plus g is integrable, and it equals the sum of these two integrals. So the idea here is that this seems so obvious to us because we've worked so much with the antiderivatives. It's a natural thing to do, but we do need to make sure that it is consistent with the definition of the Riemann integral. So let's look at number one here. So we'll take a positive epsilon, then by definition there is a delta such that for any partition, this is what we call big delta of AB, the norm of the partition is less than the delta. That is, it's refined enough so that when we look at this Riemann sum where the c sub i's are taken in each ith subinterval, just like we did when we did the area of a region using the Riemann sums. It's fine enough so that when we take the difference between the actual integral of f and the Riemann sum, it can be made less than epsilon divided by the absolute value of k. We have a lot of flexibility with this, just like we had with basic limits at the beginning of the class. So again, we have this flexibility because we know f is Riemann integrable. And then there's obviously a reason for this. We can now look at the Riemann sum of kf. And then we're going to suppose that its limit should be k times L1, where L1 is the Riemann integral of f. And so when we look at this particular term in absolute value, the first thing we want to do is factor the k from the sum and from the L1. That gives us this expression. And then, of course, the absolute value of a product is the product of absolute values. So now we can write this expression. But this is very good because we know we have an upper bound for this particular expression here, which is this. And so we get that this expression is less than the absolute value of k times epsilon divided by the absolute value of k, which is epsilon. So if f is integrable, then we're showing that kf is integrable. We know what its value is, and we can make clearly the Riemann sum as close as you like to k times L1 as we've shown here. So number one is valid, and of course we always thought that, but we still need to, like I say, we need to verify these things. Now for number two, we're going to take an epsilon again. Now we're going to assume the existence of two partitions. That is, there'll be two partitions, delta 1 and delta 2 of AB, such that for any partition delta here, just any chopping up of the interval AB, if the union of these two partitions is contained in delta, that is, this is fine enough to contain both of these partitions of AB, and we're taking the c sub I in the I subinterval, then we can make the Riemann sum of f within epsilon of 2 over L1, and we can make the Riemann sum of g within epsilon over 2 of L2. So basically what we have here is we know that these partitions exist, and we want to frame this in a way so we can write a very neat Riemann sum. So this is basically taking the definition and modifying it in a way so that we can get a clean expression here. Now, of course, we're going to do just like what we did here. we're going to look at the Riemann sum of f plus g, and we're thinking that we can make this arbitrarily close to L1 plus L2. So what we're going to do is we're going to break up the sum and connect the Riemann sum of f with L1 and connect the Riemann sum of g with L2 as we've written here. So we've got the difference with the Riemann sum of f with L1 and the difference with the Riemann sum of g with L2, just like we need in the definition of the Riemann integral. And so now we have the absolute value of a sum by the triangle inequality. This will be less than or equal to the sum of the absolute values. So now we've split these up, and we're back up here where we know we have upper bounds for this expression, and we have upper bound here for this expression. So this one is bounded above by epsilon over 2. This expression is bounded above by epsilon over 2, and that equals epsilon. So again, by assuming the existence of the Riemann integrals of f and g, we have shown that we can make, in this particular case, the Riemann sum of the sum arbitrarily close to the sum of L1 and L2. And therefore, when we look at 1 and 2, we're seeing that we're getting results that remind us of the antiderivatives, and there's no difference. Limits or no limits. With no limits, the antiderivative takes care of the linearity. When we have limits, the Riemann integral takes care of the linearity. And we are done.